Hi all, today we start discussing module 2, chapter 6, the Gauss map. The Gauss map is meant for the measurement of the curviness of surface in Rn or any n surface in Rn plus 1. The first module we have discussed what is a level set and how to define a surface using the regular points. And the last chapter we have discussed how to define a normal vector field on a n surface. So we start with an oriented n surface, that is a unit normal vector field is defined on that surface in Rn plus 1. So that is this n is what we call the normal vector field defined on that n surface. Then this n assigns at every point of the surface and assigns a unit normal vector n of p. So this is the corresponding vector. Then the map n from S to Rn plus 1. At each point of S, we assign at each point of S a vector unit normal vector n of p, like this vector field. So that is always an element of Sn, because this is the unit normal vector. Since it is the norm of this vector is 1, you can get that each n of p is an element of Sn. So this map is what we called Gauss map. So the Gauss map is nothing but the vector in the vector part of P is what we call the Gauss map. So n may be thought of as a map which assigns to each point of S, each point P of S, the point in Rn plus 1 obtained by translating the unit normal vector n of p to the origin. That means this, when you consider this vector n of p at the origin, then that is the image of p. This is one of the examples. When you consider this surface in R2 and this is our S1, you can consider this is our S1, this is the unit circle. So when you consider at each point P of S, you consider n of P. So this n of P is P comma n of P. This n of P is the vector defined at this point. So this is the n of P. So you translate this vector at the origin. So you can get this vector. And if there is another vector like this, you need to translate that vector again here. And here you can get this vector. If this is the normal unit vector at this point, you can translate to the origin again. And if this is another vector, so you can translate that to the origin again. So you can get so many points on this Sn by translating these vector to the origin. So these points are called the image of this n, or image of the Gauss map. So this give the idea of or measurement of the curviness of this, how this normal changes as we move along this S. That is the idea of the Gauss map. So this in some sense this will give the measurement of curviness of this surface looking into this unit circle or unit n sphere in Rn plus 1. This is another examples. The second example. So when you translate all these vector to this point, you can consider this much point will give the image of this Gauss map. The Gauss map is defined from each point or S2 the unit. This is the unit circle again in R2. So this is the case when n is equal to 1. This is example for n is equal to 2. If n is equal to 2, you can consider the unit sphere in R3. So this is what we defined as S2. Actually, this is our S2. So S2 resides in R3. Okay. Now you translate all this vector of the surface to origin, you can get this much portions or this much points of the S2. So this is what we called the image of the Gauss map. Then you can say that this how this surface curved in R3 looking into these points. This much curviness is there. So this is the idea of the Gauss map. Now we have a theorem. Let S be a compact oriented connected n surface in Rn plus 1. exhibited as a level set f inverse c of a smooth function f from Rn plus 1 to R with del f p not equal to 0 for all p belongs to S. Then the Gauss map maps S onto the unit sphere Sn. Okay, that means this is the sufficient condition for getting this Gauss map is onto. So in order to get this Gauss map is onto, you need to choose a surface which is compact, connected, and oriented end surface. So the image when you consider this surface, that will give the onto map. This Gauss map as onto map. Now we can prove this theorem. We need to prove that this Gauss map denoted by n, this is from S to Sn, is onto. We need to prove this map is onto. So we need to we choose a vector v in Sn. That v belongs to Sn means the norm v is equal to 1, and we will find a point, at least one point in P in S, the point P in S, such that n of P is equal to v. This will prove this map n is onto. So in order to get the pre-image of a point in Sn, we start with a vector v, which is this v whose norm is 1. We start with this vector. Now define a map from Rn plus 1 to R defined by this v, that is defined as g of p is equal to p dot v. Okay, so if we take v as this a1 a2 etc n plus 1, this g defines the map g of x1 x2 xn plus 1 is equal to this dot product. This is the dot product of p and v. P is this point, this constitute p, and this is our v. Then you can say that p dot v is equal to this one. So obviously this is a polynomial. So polynomial in x1 x2 etc xn plus 1. So this is a smooth function since it is a polynomial function. So this is continuous as well. Now we consider, as we know, you can consider the level set of this G. One particular level set is G inverse C. So this will give a set of all x1, x2, etc., x2, etc., xn plus 1, such that this is equal to C. Okay, that is a1 x1 plus etc. an plus 1 xn plus 1 is equal to 1. This is the way we construct the level set of G. So when you consider the different level sets, you can get this a1 x1 plus etc. an plus 1 xn plus 1 is equal to some c1. Similarly, this is equal to some c2. So these are all parallel planes. You can say that this is equal to 0 is also a plane. So when you consider these are parallel planes which are parallel to this v perpendicular. That is because when you consider this plane a1 x1 plus etc. n plus 1 xn plus 1 is equal to 0. So this is the plane which is orthogonal to this v, and all these level sets are planes which are parallel. Hence those are parallel to this v perpendicular. That is the idea of this the geometry of this G. Now since S is compact, you can consider this G restricted to that S to R rather than Rn plus 1 to R. So once you consider this map, so this is the restriction of G to the connected compact set. So this G attains its maximum and minimum on S, say P and Q respectively, because every continuous function defined on a compact set attains its maximum and minimum. So when you then using the Lagrangian multiplier theorem, del Gp is equal to lambda times del Fp. Okay, now you evaluate del Gp. Del Gp is the vector p comma that is obtained by dou G by dou x1. So that will give a1, dou G by dou x2, that is a2. So the vector part is a1 at etc n plus 1. Hence del Gp is nothing but p comma v. That means del Gp assigns v at every point p. Now you consider this equality. This is equal to this one. When you consider this del of p by norm del of p into norm del of p, you can consider del of p by norm del of p as n of p, and the norm del of p is also here. And the other thing constitute the one possible way of writing this is we write this is equal to lambda times norm del of p by del f p by norm del f p. This is norm del f p again, del f of p to del f of p. Okay, so this part will give plus or minus n of p, because we can say that in every connected surface there exists at least there is at the most two normal orientation can be defined on that surface. So that is either del f p by norm del f p or minus of that. So this constitute plus or minus n of p. Then you can that plus or minus can be exhausted to this lambda. Then you can write this x n of p. This is our n of p into norm del f of p into lambda, or plus or minus lambda, both everything are same. This lambda and this norm is real quantities. There, now by taking, as we know, this v is a vector with norm 1, and this n of p is also a vector with norm 1. So when you consider a norm on both sides, you can get more or less of this will be 1. Okay, by considering norm on both sides. So you can get the norm of this is 1 and norm of this vector is 1. So you can say that more or less of this is plus equal to 1. But these are real quantities. So the only possible values of this part is plus or minus 1, because modulus is always 1, and this is nothing but a real number. So you can connect this n of p, the vector part of the right side, which is equal to plus or minus v. Okay, this is the only possibility. Okay, similarly, you can get n of q is also plus or minus v with the same arguments. So our intention is to get a pre-image of this v. Okay, now we got n of p is equal to plus or minus v, and n of q is equal to plus or minus v. Once you prove, our claim is this n of p is not equal to n of q. Once you prove this, you can say that either n of p is equal to v or n of q is equal to v. Okay, that this shows that the v has a pre-image. So our intention is to prove this n of p not equal to n of q. Okay, that is the remaining part. We have n of p is equal to plus or minus v here, and n of q is equal to plus or minus v. Now we will prove the this is not equal. Okay. Now to prove this, we construct a map with some properties, and consequently we prove that this n of k never be equal to n of p. We prove this by constructing this alpha. Alpha is a, we will construct this alpha later. Once you construct this alpha, what are the consequences of this function? We constructed the alpha from ab to rn plus 1, which is differentiable at a and b and continuous on every point on this interval. The differentiable at a means differentiable on the right hand side of this. Differentiable at b means differentiable in the left hand side. Left limit and the function value will be derivative, left derivative will coincide with that. So what are the conditions? We construct alpha in such a way that alpha of a is equal to b and alpha of b should be coincided with q. Alpha dot, the velocity vector, this alpha dot of a should be coincided with this, and alpha dot b again coincided with this one, and alpha of t will not be a point of s for all a less than t less than b. Once you constructed such a curve, you can easily prove that this n of p never be equal to n of q. Because once suppose we have constructed this alpha, then we know that there are only exactly two possibilities for the normal vector field. First, you assume this normal vector field is del f by norm del f. If this is the case, we can say that alpha composition, f composition alpha, derivative of that at a. What is f composition alpha? This alpha is a function from ab to r, and f is a function from rn plus 1 to r. Okay, then what is f composition alpha? This comes from ab, the domain of alpha, to r. So this is a real function. Okay, this f is from rn plus 1 to r, and alpha is from ab to, again, the subset of r to rn plus 1. So this, the derivative of this is a real function. Anyway, alpha, f composition alpha is a real function defined on a closed interval. Then find the derivative of this function at the point a. That means the right hand derivative. Okay, that's the only possibility. Left hand derivative is not there. So what is the derivative? That is obtained by using the chain rule. This the d by dt of f composition alpha. that is equal to del f of alpha of a dot alpha dot a. Then del f of alpha of a is equal to norm del f of by considering the norm divided and multiplied by norm, you can write this as norm del f of p into n of p. That is because of this del f of p, del f of alpha of a divided by norm of del f of alpha of p into norm del f of alpha of b, that is alpha of a, that is alpha of, that is p. So we can consider this as our norm, the normal vector field defined in this case. So we can write it as n of p into norm of del f of p dot alpha dot we have constructed by assumption we have constructed alpha in such a way that alpha dot is equal to p comma v, then this will be p comma v. By taking the dot product you can get this constant times n of p dot v. This is the vector part of this vector field. Okay, n of p dot v. Similarly you can prove that the derivative at b is also del f q, the point is q, n of q dot v. Okay, so this is the case. We have evaluated the derivative of this real valued function defined on AB at the point A and B. Okay, now assume we can say that this is always positive and this is also positive. Now if you assume n of q is equal to n of p, what happens? If these two quantities are same, you can say that this f composition alpha, derivative of this function at b and derivative of this function at a have the same sign. Okay, that means the function f composition alpha is either increasing at a and b or decreasing at a and b. Okay, at those points a and b, this f composition alpha has the same monotonicity. If it is increasing at a, you can say that that is increasing at b. If this happens, n of q is equal to n of q. That means when you consider this, the graph of this function f composition alpha at a and b, you can say that if this function f composite here, take f composition alpha on y-axis, and this is our corresponding t, and if you consider this function, if this is our f composition alpha of a, if f is increasing at here, you can say that this function like this. Similarly, at this point, okay, this is here. Here we have increasing nature. So that is if this is the case, we know that f composition alpha of a, this is f of alpha of a. This is equal to f of p, which is equal to c, because p is a point on the surface. Similarly, what is f composition alpha of b? This is f of alpha of b, that is equal to f of q. Q is again a point on S, because this point q is nothing but the point of minimum of that function g attained on the surface S. So this f of q is also c. So we can say that this f composition alpha at a and f composition alpha at b are the same value, say c. So we have c here. Then here the function is increasing. We can say that here also increasing. Okay, this is the first case. If this is the case, you can get a T2 here. Say this is T2. At the point T2, we can say that f composition alpha of T2 is less than c, and you can find another point T1 here. At the point T1, f composition alpha T1 is greater than c. If this f composition alpha is increasing at both points A and B, so you can easily find a point in between T1 and T2 at which this say we can say that that is T3, at which this f composition alpha is nothing but c. Okay, so that means this alpha of t is, this implies alpha of t is a point on S. So alpha of T3 is a point on this S. This is a contradiction because of 2. Yeah, the similar argument can be done using the decreasing property. In the decreasing case, we have this type of graph. This is A and this is B, and this point is our C. Then we can say that if this is this function f composition alpha is decreasing at A and B, that means the function moves like this, and here also we have decreasing nature. So this is the nature. So you can get a point T1 here and a point T2 here. F composition alpha of T1 is less than C, and F composition alpha of T2 is greater than C. So you can get in between this T1 and T2 there is a point at which this function F composition alpha attains C. So there exists some T3 with F composition alpha of T3 will give this C. Then alpha of T3 is a point on S. So this is a contradiction for this 2 again. So if in both cases, if F is decreasing at A and B, or F composition alpha is decreasing at A and B, or F composition alpha is increasing at A and B, we have a contradiction. If we assume this n of q is equal to n of p. This shows that this once you constructed such a function alpha with these conditions, you can say that this n of q is not equal to n of p. Then one of them will give v. Hence, we can say that this Gauss map is onto. So this is the idea of proof. The only thing remains to show that this alpha can be constructed with this condition. This is the way we construct alpha. Suppose this is our surface S and enclose S in the interior of a large sphere S1. So this is our this sphere is S1 and this is the surface closed. This is connected, compact, oriented end surface. And this S1 is our unit sphere. Not unit sphere, a sphere which can enclose this S. Okay, that is possible because this S is compact. So this is compact subset of Rn plus 1. Then this is closed and bounded. Then you can construct such a large sphere S1. In order to construct alpha, we first construct three functions: alpha 1, alpha 2, alpha 3. So the alpha 1 of t is defined as p plus t times v. Okay, this p is this point, and tv, this is the linear function. So this is an equation of a straight line which passes through this p and parallel to this v. This is the definition of the straight line, passes through p and parallel to v. So this will give this is the vector v, and this function starts from this point, and the equation of this line is alpha 1. And you construct alpha. This a1 is such that alpha 1 of a1. That means we move from this p along the direction of v. Then you can get a point a1 at such that this alpha 1 of a1 intersect with this sphere, and we call this point as alpha 1 of a1. So where a1 is such that alpha 1 f1 belongs to s1, and define s2 alpha 2. Alpha 2 is defined as q minus tv. If this is the v, then we move along the reverse direction of v from q. So this is the equation of the straight line passing through q and in the direction of minus v. So we can move along this way. Then we can easily find a point a2 such that alpha a2 intersect with this sphere s1. So we call this point as a2. That means alpha to a2 is this point. Now we can get 2 points, alpha to a2 and alpha 1 a1. Both are on the large sphere s1. But we know that S1 is a connected set. So you can easily find a continuous path, say alpha 3 along this or a path on this S1. So you can say that this path S1, this path of path connecting this alpha 1 A1 and alpha 2 A2 does not intersect with this S, because this path lie only on this S1, and S1 is the large sphere which encloses this S. So clearly this alpha 3 does not contains any point on the surface S. So using these 3 points, these 3 functions alpha 1, alpha 2, alpha 3, we construct alpha of t. What is alpha of t? Alpha of t is alpha 1 of t. That means the alpha of t starts from this and move on this way and intersect with here and follow this path to reach this point and trace this curve in the reverse direction. Okay, so that is the idea. Alpha 1 of t from 0 t 0 less than equal to t less than equal to a1, and from the a1 you can define alpha 3. So move along alpha 3. So that is alpha 3 of t1 plus b1 minus a1 from a1 to this point. From this point we use alpha 2 in the reverse direction. So we trace alpha 2. We trace this path of alpha in the reverse direction. That's why here minus t. This number minus t. Okay. So that is the reverse direction of v. So this constitute alpha of t. Okay. Now we need to verify that the given conditions are satisfied. So for that we first evaluate alpha 1 of t. Alpha 1 of t does not belong to, the first thing is we need to find points a, b such that here the point a is for the domain of alpha we have to set the closed interval. So the closed interval here is a is 0 and b is this final point. Okay. Now we can verify all this. The first thing is, the first two conditions are very easy to check. Alpha of 0, alpha of a, that is 0 here. Alpha of 0 is alpha 1 of 0. Alpha 1 is nothing but this is alpha 1 of t here. Alpha 1 of t is equal to p plus tv. Okay. Then alpha 1 of 0, that is alpha of 0. Alpha 1 of 0 is equal to p, and alpha of b. Alpha of b means alpha of the last point, that is alpha 2 of what is b here? B is this one. Okay, we substitute for t this value a1 plus a2. That means this minus again the same quantity, that is alpha 2 of 0. What is alpha 2 of 0? Alpha 2 of 0 is equal to q. Okay, then we can get alpha 1 of a equal to, that is alpha 1 of 0. This is our domain. The domain is 0 comma this point a1 plus a2 plus b2 minus b1. Then alpha 1 of 0 is equal to p, and alpha 2 of this is alpha of a, and alpha of b, that is alpha of this point, that is equal to q. So first two conditions are same. Now we have to verify alpha dot of a, that is the derivative of alpha at a. So that is obtained by taking the derivative of alpha 1. When you take the derivative of alpha 1, you can get v. So that will give the vector v at the point p. Okay. Now alpha dot of b, so that is obtained by taking the derivative of this, that is alpha derivative of alpha at this point. So that is derivative of this function alpha 2 of this quantity. So derivative is alpha 2 of this. So what is alpha 2 of this one? That is defined as alpha 2 of, the derivative of alpha 2 is nothing but this minus t. This is minus v, alpha 2 of b minus t, right? This is equal to this one. So what is the derivative? Derivative is minus times minus v, that is again v. So we can get alpha 2 or alpha of b as v again. So alpha dot of b is equal to, that is at point q we have the same vector v, because the derivative of this function is derivative of alpha 2 into this minus 1, and derivative of it is minus v. So minus of minus v will give v. Okay. Now we have to verify the second condition. Alpha of any t is outside this S for a less than t less than b. Okay, that means 0 less than t less than this point. We have to prove that alpha t does not belong to, does not lie on surface. So first we have verify alpha 1 of t. Alpha 1 of t does not belong to S for t greater than 0. At t equal to 0, we can say that alpha 1 of t is p. So that is on the surface. This greater than 0, we can get this is not a point on S. Why it is not a point on S? we consider this G composition alpha 1 dash t. We consider a new function G composition alpha 1 dash of t. Okay. So this G composition alpha 1 is a function from 0 to our b. What is b? A1 plus A2 plus B2 minus B1 to R. It's a real function. And what is the derivative? That is obtained by del G alpha 1 of t dot alpha dot t. That is v dot v. That is always that is norm 1, norm v, that is equal to 1, which is greater than 0. So G is increasing along alpha 1. So we know that alpha 1 of 0 is this p. Therefore, we can say that G of alpha 1 of 0 equal to C, because G of this is G of p. This is not equal to C. This is our some D. That is G of this is P. G of P is equal to D. That means G. We know that P is the point of maximum. Okay. So G of P is equal to D means G attains the maximum value at P, that is equal to D. Now G is increasing along alpha 1. So G attains the values which are greater than D. Okay. We can say that if you consider any point some P dash, you can say that that is some D1 which is greater than D. So obviously this P1 does not belong to the surfaces, because P is the point of maximum. Once point of maximum of G, once G attains a value which is greater than this D, we can say that that point never be a point on S, because P is the point of maximum. So we can say that no point after this t equal to 0, this alpha 1 of t does not belong to S. Similarly, alpha 2 of t. Okay, see, if t greater than 0, what is the derivative here? Derivative is v dot minus v, using the same argument. So G is decreasing. Okay, this is negative number, so G is decreasing along alpha 2. But we know that the minimum value of G composition alpha 2 of the point, this is alpha 2 of 0, that is equal to G of Q, say that is some E1. This is the minimum value. Now if you take any point G of Q prime which is less than E1, we can say that this Q prime does not belong to S, because this Q is the point of minimum. But we know that G composition alpha 2 is decreasing. Okay, so we can say that no point on alpha 2 lie on the surface S. Similarly, obviously this alpha 3 does not belong to S, because alpha 3 is a path in the large sphere which fully encloses this surface inside the whole sphere. Okay, so from these three conditions you can say that this alpha of t does not belong to or does not lie on the surface for a less than 0, that is 0 less than t, not a less than 0, 0 less than t, less than the point b, that is a1 plus a2 plus b2 minus b1. Okay, this proves this proves the construction of alpha with the desirable properties. So then as a consequence we can say that n of p not equal to n of q. Then at least one point p or q, we can get n of that point is equal to v, which shows that every v on Sn has a pre-image, which shows that the Gauss map is onto.